Hello there. I'm glad you wandered into this small pocket of quiet. Outside, the night stretches wide and dark, sprinkled with a few patient stars. Somewhere beyond that gentle sky, beyond our galaxy's slow turning, there is a deeper place where everything began and everything is still unfolding, a hidden heart of the cosmos. Tonight, we'll drift there together in stories, following the threads of light and gravity inward, toward the very center of the universe as we understand it, and as we're still learning to. We'll move slowly, like a conversation shared in low voices, tracing how distant galaxies, invisible matter, and the faintest ancient glow all whisper the same tale of origin and connection. If this kind of soft, curious wandering keeps you company, you're welcome to like the video or subscribe for more quiet nights like this. For now, let your awareness settle and grow heavy, like a pearl dropping to the sea floor. There's no rush. When you're ready, we'll begin this warm, inward voyage together. Out in space, distance stops behaving like something you can walk or drive or fly across. It stretches into numbers so large they feel almost empty, even when you know each one is describing a very real gap between worlds. The darkness between stars is not just night. It is a vast, cold ocean where even light needs years to cross from one shore to another. Our minds are built for rooms and roads and horizons you can see, not for gulfs measured in tens and hundreds of billions of miles. It is no wonder that when we try to imagine the scale of the universe, it slips through our fingers like water. And yet, even with these limits, we have found ways to reach out. We build instruments that can drink in the faintest traces of light from galaxies millions of light years away. We send small, quiet machines to travel for us, letting them drift far beyond the places any human has ever stood. With their help, the cold emptiness becomes a little less abstract. It gains landmarks, a planet here, a ring of ice there, a thin boundary where the breath of our sun meets the wider wind of the galaxy. If you picture that journey as a slow, gentle glide outward, our first stop lies surprisingly close to home, at least in cosmic terms. Somewhere in the dark, far past the orbits of the familiar planets, a handful of tiny messengers are still moving steadily away from the Sunday. They are old now, by spacecraft standards, but they are not lost. They carry with them the stories of the places they have seen, and even if their voices are fading, the paths they follow can guide our imagination outward. One of these travelers is New Horizons. It left Earth in January of 2006, a bright point on the end of a rocket aimed at the dim, icy edge of the solar system. Its main destination was Pluto and its large moon, Charon worlds that, for most of human history, were nothing more than shifting points of light in a telescope. To reach them, the spacecraft needed both patience and a gentle push from one of our giant neighbors. On its way outward, New Horizons swung past Jupiter and used the planet's immense gravity as a kind of slingshot. Instead of firing more engines, it simply fell toward the gas giant and then let that fall bend its path and increase its speed. In doing so, it saved years of travel time. While it was there, it did not hurry through. Its cameras lingered on Jupiter's banded clouds and its family of moons, sending home detailed images of storms, auroras, and swirling patterns that had only ever been seen as blurry smudges before. Among those moons is Io, a world of fire orbiting a world of gas. New Horizons caught something no one had filmed so clearly before. A volcano on Io in the middle of an eruption, throwing material high above the moon's surface. It was a brief, fierce gesture in the deep cold of space, a reminder that even in distant corners of the solar system, there are places that are geologically alive, reshaping themselves in silence. After this meeting with Jupiter, the probe continued on its long arc toward the dim sunlight of Pluto. In early 2015, almost a decade after leaving Earth, New Horizons finally arrived in the outskirts of that small, distant system. It did not stop, it raced through at high speed, but in that brief passage it turned its instruments toward Pluto and Charon from every angle it could. It made maps of their surfaces, traced the patterns of bright plains and dark patches, and watched how sunlight scattered from ice and rock. The spacecraft also listened in quieter ways. It measured the thin, fragile atmospheres around these bodies and how they are shaped by the solar wind, a stream of charged particles breathing outward from the sunday. It sampled the magnetic environment and studied how invisible fields wrap around these remote worlds. It even searched carefully for any hidden moons that might have been too small or faint for earlier telescopes to see, and helped refine Pluto's orbit, tightening our understanding of where exactly it travels through space. When that main part of its mission was complete, New Horizons did not simply fade into irrelevance. It kept going, drifting beyond Pluto's path and deeper into the Kuiper Belt, the wide, icy ring of small bodies that encircles the outer solar system. There, it visited another object, a snowman-shaped relic of the early solar system, now known as Arrokoth. By photographing and studying this quiet, red-tinted world, the probe gave scientists a rare glimpse of the kind of building blocks from which planets once grew. Even after that encounter, New Horizons continued to send back measurements not just of distant objects, but of the space between them. It helped us gauge the distances to nearby stars, like Proxima Centauri and Wolf 359 more precisely, using the subtle change in viewpoint as it moved farther from the sunday. But on board, its power source is slowly weakening. The spacecraft carries a radioisotope generator, a kind of long-lived battery that turns the heat of decaying material into electricity. As the years pass, that power will dwindle. Sometime around the late 2020 seconds and into the 2030 seconds, one instrument after another will have to be turned off, like lights going out in a house at night. By the time New Horizons is roughly 100 astronomical units from the Sun, 1 astronomical unit being the average distance between Earth and our star, its generator will fall silent. Radio contact will fade. The spacecraft will no longer be able to speak to us, but it will not stop. Following a gently curving path that never bends back, it will slip across the boundary of the solar system and into the thin, unmarked dark between the stars. It will not be the first to do so. Long before New Horizons, 2 other probes quietly claimed the title of humanity's first interstellar messengers, Pioneer 10 and Pioneer 11. They were launched in the early 1970 seconds, at a time when images of the outer planets were mostly artists' impressions and distant photographs, blurred by Earth's atmosphere. Pioneer 10 left Earth in March of 1972, heading for Jupiter. After about a year and a half of travel, over 600 days threading through the inner and middle solar system, it arrived in the giant planet's realm in December of 1973. From there, it sent back close-up views of Jupiter's thick cloud tops and its larger moons, turning mysterious points of light into detailed worlds with weather, structure, and texture. Its instruments also tasted the invisible environment around Jupiter. They measured the planet's powerful magnetic field and sampled the charged particles trapped within it. They studied the atmosphere, and helped reveal a surprising fact. Jupiter gives off more heat than it receives from the Sun, glowing with internal energy left over from its formation and from the slow compression of its massive bulk. These early measurements laid the groundwork for much of what we now understand about gas giants and their families of moons. Pioneer 11 followed a similar path at first, also swinging by Jupiter, but its main destination was Saturn, the other great ringed giant of our system. As it flew past, it recorded the shape and strength of Saturn's magnetic field and sent home images of the planet's rings and several of its moons, including Titan and Mimas. For the first time, humanity was seeing these places not as distant, pale dots, but as real landscapes of ice, haze, and shadow. Once their primary missions were done, neither Pioneer probe turned around. Both simply kept moving, coasting outward on escape paths that carry them farther from the Sun every year. The last faint whisper from Pioneer 11 reached Earth in the mid-1990 seconds. The final signal from Pioneer 10 arrived in 2003. Since then, they have been radio silent, still racing through space, but now too far and too weak to be heard. Their distances are measured in hundreds of astronomical units and growing. There are other travelers, too, that have gone even farther and faster. Voyager 1, launched in September of 1977, also set out toward Jupiter and Saturn. Along the way, it transformed our picture of the outer solar system. Its cameras revealed that Jupiter is not just a striped ball of gas, but a restless world with a thin ring system and many more moons than we had known. It caught volcanoes erupting on Io, just as New Horizons would later do, and showed that the Great Red Spot is not a static blemish, but a massive, churning storm larger than Earth. Passing Saturn, Voyager 1 continued to gather images and data, but its true distinction came later, long after it left the realm of the visible planets. As it crossed the orbit of Neptune and moved toward the edge of the Sun's influence, its instruments began to feel a change in the environment. The charged particles around it shifted in energy and direction. The spacecraft was approaching and then crossing the heliopause, the boundary where the outward flow of the solar wind gives way to the steadier pressure of the interstellar medium. This heliopause is not a solid wall or a sharp line. It is more like a vast, uneven shell around the Sun, where the two winds, the suns and the galaxies, press against each other. In this region, magnetic fields twist and reconnect, and the thin plasma of space forms delicate, invisible structures. Voyager 1 was the first human-made object to cross this frontier and send back direct measurements of what it is like there. Beyond the heliopause lies the scattered outer architecture of our system, and farther still, the inner edge of the hypothetical Oort cloud, a distant reservoir of icy bodies that may encase the solar system like a loose, dark halo. Voyager 1 is on a path that will eventually carry it into that deep, quiet realm. It is the most distant and fastest of all our spacecraft, drifting through a darkness so complete that the Sun itself is only a bright star behind it. When you think about these probes, New Horizons, the Pioneers, Voyager 1, it can be comforting to imagine them not as lost machines, but as tiny, persistent markers of our curiosity. Each one has carried us a little farther from home, turning distant points of light into places with weather and history, and helping us trace the outline of the invisible bubble our Sun blows into the galaxy. They are still moving outward, carrying with them a simple truth. From one small planet around an ordinary star, it is possible to reach into the vastness and listen very quietly to what the universe is made of. Studying these distant travelers is one of the soft, hidden keys to understanding how that universe behaves. They are tiny, but they have crossed boundaries we can only imagine, and their instruments have felt things no human hand has ever touched: the thin breath of interstellar space, the edge of the sun's influence, the faint whisper of particles drifting between the stars. Through them, we begin to see how our own small system is cradled inside a much larger sea. Their time as active messengers, though, is limited. On board, each carries a power source that works like a very long-lived ember, a radioisotope generator that slowly turns the warmth of decaying material into electricity. That ember was bright enough to last for decades, but not forever. Around the middle of the 2020 seconds, the power available to Voyager 1 drops so low that one instrument after another must be shut off, like lamps being dimmed in an old house at night. At some point, there is not enough energy to run the transmitter at all, and the spacecraft falls silent. From our point of view, the connection is gone. Silence, however, does not mean the journey stops. Voyager 1 continues coasting outward, untouched and unhurried, its path set long ago. In a few centuries, a span of time that feels immense to us, but is only a heartbeat on galactic scales, it is expected to reach the inner edge of the Oort cloud, that vast, hypothetical halo of icy bodies that may surround our solar system like a distant, dark fog. Passing through that region is not a matter of days or years, but tens of thousands of years. Roughly 30,000 years from now, if nothing disturbs it, Voyager 1 will have threaded its way through that outer reservoir and stepped fully beyond what we usually mean when we say the solar system. Even then, its story against the starry background is not finished. About 10,000 years after it clears the Oort cloud, it will pass relatively close, in cosmic terms, to another star, a faint sun known as Gliese 445. Close here still means a distance of about 1.5 light years, far enough that the star would simply be another pinprick of light on whatever sky the spacecraft sees. There will be no dramatic encounter, no swooping dive past planets, just a long, slow glide by. After that, Voyager 1 will keep going, its metal slowly cooled to the temperature of the deep dark, its golden record still bolted to its side, drifting into reaches of the galaxy where no one knows its name. Whenever we speak of Voyager 1, a part of our attention naturally turns to its twin. Voyager 2 left Earth a few weeks earlier, in August of 1977, on a slightly different path that would let it visit more of the outer planets. Like its sibling, it swung by Jupiter for a helpful pull of gravity, but its grand tour included Saturn, Uranus, and Neptune as well. Along the way, it carried our curiosity past worlds we had barely glimpsed before. At Jupiter, Voyager 2's cameras watched over the shoulders of its twin, deepening our view of the giant planet's storms and moons. It was from the combined Voyager data that scientists grew more confident in the idea that beneath the icy crusts of moons like Ganymede and Europa, there might be deep, hidden oceans, water kept liquid not by sunlight, but by the tides inflexing from their massive planet. Instead of blue skies and open seas, these oceans would lie in darkness, beneath kilometers of ice, warmed from below. No one knows yet what, if anything, stirs in those depths, but the very possibility changed how we think about where life might find a foothold. At Saturn, Voyager 2 took the measure of another gas giant. Its instruments felt the strength of the planet's magnetic field and sampled the charged particles that swirl around it. Its cameras sent home scenes of Saturn's rings casting delicate shadows on the cloud tops, and of small moons tucked into gaps and edges like shepherds guiding flocks. Several previously unknown satellites revealed themselves in those images, tiny but real, adding complexity to a system we had once pictured as simple rings around a yellow planet. Then came Uranus and Neptune, the colder, more distant giants. Before Voyager 2, these worlds were little more than pale disks in telescopes, smooth and featureless. The flybys changed that. Uranus appeared as a tilted, muted globe, its axis almost lying on its side, with a faint ring system encircling it and a set of moons that showed surprising variety. Neptune emerged as a deeper blue, with a great dark storm swirling in its atmosphere, and thin arcs of ring material looping around it. In total, Voyager 2's journey past these planets revealed 17 new moons and confirmed that both Uranus and Neptune have rings of their own. The outer solar system, once imagined as quiet and simple, suddenly looked busy and intricate. As it passed Neptune, the planet's gravity gently redirected Voyager 2's path, tipping it out of the flat plane where most of the planets orbit. From then on, the spacecraft no longer had a chance to visit any other major worlds. Instead, its road led away from the familiar disk of our system and into a more three-dimensional view of space around the Sunday. That new angle brought its own kind of treasure. From its high, slanting trajectory, Voyager 2 has been sampling the environment of the outer heliosphere, the bubble carved out by the solar wind, that continuous stream of particles flowing from our star. It has measured the properties of interstellar plasma and the cosmic rays that filter in from the rest of the galaxy. It has helped refine the distances to nearby stars by providing another vantage point far from Earth. Like Voyager 1, it has crossed the boundary where the sun's wind yields to the broader pressure of interstellar space, giving us a second, independent glimpse of that elusive frontier. Right now, Voyager 2 is more than 100 astronomical units from the Sun, the number increasing every second as it speeds through the dark. Its future path is written on similar timescales to its twins. Tens of thousands of years from now, it is expected to pass comparatively near a faint red dwarf called Ross 248 in the constellation of Andromeda, at a distance of roughly 1.5 to 2 light-years. Much later, hundreds of thousands of years from its launch, its path will carry it within a few light-years of Sirius, one of the brightest stars in our night sky. From Earth, there will be no moment when we can look up and point to Voyager 2 as a dot against the stars. Even now, it is far too small and too dark to see directly. Our knowledge of it comes only from the radio murmurs that reach us. In the distant future, long after its power source has cooled and its transmitter has gone quiet, it will be invisible in every sense but one. It will still exist, still traveling, a tiny artifact threaded into the fabric of the galaxy. When you think about these machines on such enormous timescales, it becomes clear how early we still are in our story of space exploration. These spacecraft are like the first careful footprints on a shoreline that stretches for thousands of kilometers. We can imagine many possible fates for them. Perhaps, in some far-off era, one might collide with a wandering piece of rock or ice and be shattered into fragments. Perhaps, in a future where our descendants travel between stars as routinely as some people now cross oceans, a curious crew might one day go out to meet one of these old probes, bring it home, and place it in a museum as a relic of the age when interstellar travel was still a dream. It is also entirely possible that nothing so dramatic will ever happen. The more likely story is quieter. They simply continue drifting, their surfaces slowly worn by rare impacts from dust and by the constant, gentle hammering of high-energy particles. Over millions of years, their metal may weaken, their sharp edges soften, their structures crumble. Bit by bit, they could erode into specks, then into grains, and finally into dust mixed with the dust of stars and planets, indistinguishable from the material out of which worlds are made. Their names would be forgotten, but the impulse that launched them to know, to see, to reach a little farther, would live on in other forms. From these small messengers, it is a natural step to lift your gaze to the stars themselves. Imagine a sphere around the sun with a radius of 50 light-years, a bubble of space that our light has been filling since long before human history began. Inside that bubble lie roughly 1,400 stellar systems. Many of those systems contain more than one star, so the total number of suns in this local neighborhood climbs to well over 2,000. Some are faint red dwarfs, burning slowly and quietly for trillions of years. Others are hotter and more luminous, blazing white or blue, with temperatures and sizes that strain our intuition. There are too many to linger on each one. A human lifetime is not long enough to tell all their stories in detail, but in the gentle landscape of imagination, you can glide from one to another in moments, covering tens of light years in the time it takes to finish a sentence. Instead of rockets and fuel, you ride on thought, letting it drift along lines of starlight and data until each new system appears like a lantern in the dark. If you begin near our closest neighbor, Proxima Centauri, and then let your attention slide a little farther, about 11 light-years away, you find yourself in the faint glow of a small red star known as Ross 128. From Earth, you cannot see it with the naked eye. It does not dominate any constellation or draw poets to write about its brightness. It is modest, cool, and easily overlooked. And yet, circling this quiet star is one of the closest known Earth-like exoplanets, Ross 128b. Ross 128b is similar enough to our world that it invites a kind of cautious daydreaming. Its mass is estimated to be only a bit greater than Earth's, perhaps a third heavier. If its composition is roughly the same rock and metal, with a thin skin of air, its radius would be only slightly larger, and the pull of gravity at its surface only gently stronger. Someone standing there would feel a little heavier than on Earth, but not crushed. A step would still be a step, a jump still a jump, just with a touch more weight. The temperatures scientists infer for Ross 128b are also, in a rough way, familiar. On average, if you treat the planet like a simple ball, absorbing and radiating light, its equilibrium temperature comes out just a few degrees cooler than Earth's. That estimate hides a lot of complexity. No one yet knows the thickness of its atmosphere or its exact composition, but it suggests a world that is not frozen solid nor baked to sterility. A range stretching from deep cold in some regions to milder, potentially temperate conditions in others seems possible. This planet orbits very close to its star, much closer than Mercury does to our Sun, circling at a distance only a fraction of the Earth-Sun separation. Because Ross 128 is a dim red dwarf, its light is softer and weaker than the Sun's, so a planet must huddle close to receive a comparable amount of warmth. Ross 128b races around its star in less than 2 of our weeks, completing many years in the time it takes us to move from one phase of the moon to the next. Most likely, it is tidally locked, showing the same face to its star all the time, the way our moon always turns one side to Earth. On such a world, one hemisphere would live under an endless day, with the star sitting in roughly the same part of the sky, slowly shifting but never setting. The opposite side would be trapped in eternal night, lit only by starlight and whatever faint glow comes from the sky or the ground. Between these extremes lies a band of twilight, the dividing line between day and night that slowly circles the planet. Many people who imagine life on a tidally locked world picture this twilight zone as the most comfortable place where the heat of the day and the cold of the night might balance into something more moderate. The star at the center of this system, Ross 128, is small, with a mass only a fraction of the Sun's and a surface temperature roughly half as high. Its light would tint the sky in shades of red and orange rather than bright white. Unlike some red dwarfs, which are prone to fierce flares that can strip atmospheres and bathe nearby planets in harsh radiation, Ross 128 appears to be relatively calm. Its brightness does not spike and drop wildly. It does not seem to hurl out violent eruptions of stellar material very often. For any potential life clinging to a nearby planet, that kind of steadiness would be a blessing. There is another quiet detail that adds to the fascination. Ross 128 is moving through space in such a way that it is gradually drawing nearer to the Sunday. In tens of thousands of years, about 79,000, by current estimates, it is expected to come closer to us than Proxima Centauri is now. The map of our nearest stellar neighbors is not fixed. Over long time scales, the stars drift past one another, trading places in our list of closest suns. The universe is patient enough to let such changes play out. If from Ross 128, you let your imaginary path bend outward again, about 12 light-years away, in almost the opposite direction from the Sun, lies another small star, Lytton's star. Also known as GJ 273, it too is a red dwarf, though its light would appear with a slightly warmer orange tint. Its mass is only a fraction of the Sun's, and its radius is roughly a third as large. Its luminosity is so much lower than the Sun's that if you could trade places and stand beside it, the daylight would feel more like a gentle, perpetual late afternoon than a blazing noon. What makes Lytton's star particularly interesting is the richness of its planetary system. Despite its modest size and faint glow, it seems to host several worlds, some of them brushing against the star's habitable zone, the band of distances where, with a kind and steady atmosphere, liquid water could exist on a planet's surface. In this quiet corner of our journey, those planets don't arrive as sharp maps or photographs, but as soft possibilities, spheres of rock gently warmed by a small sun, perhaps wrapped in clouds, perhaps bare and stark, each one keeping its own quiet version of weather and climate, shaped by the slow conversation between starlight and stone. All of these places, Ross 128b, the companions of Lytton's star, the faint red suns themselves, are close in galactic terms, only a few tens of light years from our home. And yet, for us, they are still impossibly far. No probe we have built could hope to reach them within a single human lifetime. For now, they live mostly as patterns in data and scenes in the mind, stitched together from careful measurements and patient modeling. On a calm night, it can be oddly soothing just to know they are there at all. Real worlds, circling real stars, waiting in the dark while we learn, slowly and gently, how to understand them from afar. If you choose one of those quiet red suns to linger on for a moment, Luton's star is a natural place to rest your gaze. From a distance, it is so faint that it never calls attention to itself, hiding in the background of the sky, needing a telescope and patient eyes to be seen at all. Yet this modest little sun is busy. Around it, astronomers have found signs of at least 4 companions, 2 planets already confirmed, and 2 more that look promising but are still waiting for their stories to be fully written. The first confirmed planet is known as Luton B. It was not discovered through dazzling photographs, but through something more delicate, careful measurements of the way the star moves. As Luton's star circles the galaxy, its path wobbles ever so slightly under the pull of an unseen planet. From that tiny wobble, astronomers inferred that something with the mass of a world was tugging on it. Luton B is thought to be roughly 3 times as massive as the Earth, with a radius about 1/3 larger. It falls into a category we call a super-Earth, a rocky planet a bit heavier and bigger than our own. On its surface, the pull of gravity would likely be stronger than on Earth, but not crushingly so. You might feel your steps land with a little more weight, your body a little more anchored, but you would still be able to move, to walk, to look up. The orbit of Luton B brings it close to its star, at a distance only a fraction of the Earth-Sun separation. But because Luton's star is cooler and dimmer than the Sun, that closeness does not automatically condemn the planet to a furnace-like fate. Calculations suggest that the amount of light and heat reaching Luton B is roughly comparable to what Earth receives. In the simple language of energy, it lies in the habitable zone, the range where, under the right conditions, liquid water could exist on a planet's surface. If you reduce all the complexity of weather and atmosphere to a single number, you get an equilibrium temperature. For Luton B, that number seems to fall in a range that, translated into everyday terms, runs from a crisp winter's day to a cool spring afternoon. On the cold side, it might feel like a place of long frosts. On the warm side, like a world where the air has a gentle, chilly bite, but is not unbearably harsh. Of course, everything depends on whether the planet actually has an atmosphere and what that atmosphere is made of, but the raw sunlight it receives is not wildly hostile. Because of this, Luton B has become one of the closer and more intriguing candidates in the search for planets that might, in theory, host life. Not a twin of Earth, but a cousin, a little heavier, a little larger, circling a smaller, redder star. The other confirmed planet in the system is Luton C. This world is thought to have a mass comparable to Earth's, but it hugs the star much more tightly. It races around in less than 5 days, completing a year in the time it takes the moon to move through a small portion of our sky. That closeness means far more intense heating. The planet almost certainly lies well inside the comfortable zone, in a region where starlight beats down with enormous power. On a world like that, any atmosphere it might once have had could be stripped away or baked off over time. One side of the planet is likely in perpetual glare, the other in endless darkness. Because so close to a small star, tidal forces tend to lock a world so that one face always points toward the light. It makes for a dramatic image, a baked, bright hemisphere and a frozen, shadowed one, separated by a band of twilight where the star forever hangs on the horizon. Farther from the star, hints of 2 more companions have appeared in the data. These candidates, not yet fully confirmed, seem to be larger, colder worlds, ice giants with masses several times that of Earth, perhaps up to 10 or 15 times as heavy. Their orbits lie beyond the star's habitable zone, circling at distances where the faint warmth of the red dwarf cannot melt the deep cold. Their years would last many hundreds of days. If they exist as suspected, they are likely wrapped in thick, icy atmospheres or layers of frozen material, more like scaled-down versions of Uranus and Neptune than enlarged Earths. Together, these planets, confirmed and candidate, paint a picture of a small, cool star with a varied system, a potentially temperate super-Earth, a hot, close-in sibling, and distant, frozen giants, all circling a sun that, from far away, looks like almost nothing at all. If you let your attention drift onward, another star steps forward from the background, Altair, about 17 light-years from Earth. Unlike Luton's star, Altair is hard to miss. It is a bright, white-blue beacon in our night sky, shining with more than 10 times the sun's luminosity. Young, on cosmic timescales, it burns hotter and faster than our own star. One of the most striking things about Altair is how quickly it spins. While the sun takes about a month to turn once on its axis, Altair manages a full rotation in less than 9 hours. The gas at its equator rushes around so fast that the star's shape is pulled outward. Instead of being a perfect sphere, Altair is noticeably flattened, bulging at the equator and narrower from pole to pole. This distortion changes how the star shines. At the poles, where the surface is closer to the center and the gravity stronger, the material is compressed and heated more, reaching higher temperatures. At the equator, where the pull is weaker and the surface is flung outward, the gas cools a bit. The result is a star whose poles are hotter and brighter, and whose equator is comparatively cooler and dimmer. For a long time, this was only a prediction based on models and calculations. Then, using a network of telescopes acting together like a giant lens, astronomers produced an image of Altair's surface. Its squashed outline was confirmed, making it the first star beyond the Sun whose distorted shape we have directly seen. Around Altair, astronomers have found no clear evidence yet of planets. That does not mean none exist. It only means that with our current tools, none have been firmly detected. There are, however, signs of something else, a diffuse ring or cloud of dust and gas encircling the star. Starlight scatters through this material, creating a kind of luminous haze. In a sense, Altair wears a vast, delicate halo, and the scattered light acts like a veil, blurring the star's signal, the way fog softens edges. Even so, Altair remains one of the most studied bright stars in our neighborhood, a fast-spinning, oblate lantern lighting up that part of the sky. Farther out, about 25 light-years from Earth, lies another intriguing system, Fomalhaut. For a long time, the three main stars associated with this name were thought to be separate, unrelated points of light, sharing only a patch of sky. More recent observations have shown that they are, in fact, bound together by gravity, forming one of the widest multiple star systems known in our vicinity. The farthest components are separated by several light-years so far apart that, if you could project their positions onto our sky, nearly a dozen full moons could fit between the most distant pair. The brightest and best-known member is Fomalhaut A, the star that people have meant when they spoke of Fomalhaut since ancient times. It is a young, hot star with a mass roughly twice that of the Sun and a radius nearly twice as large. It shines with a light far more intense than our stars, and its surface temperature is high enough that its glow leans toward white and blue. despite its youth, Fomalhaut A is already well into a fast life. Stars of this mass burn through their fuel more rapidly than smaller suns. Current models suggest it may live for around 1 billion years before evolving into a very different state and eventually ending as a dense white dwarf. For now, though, it sits in a luminous stage, surrounded by a wide, dusty ring. This ring is not a neat, thin hoop like Saturn's. It is a broad belt of gas and dust, divided into segments, with an inner edge far from the star, more than 100 times the Earth-Sun distance, and a width spanning tens of astronomical units. In this vast annulus, smaller bodies are constantly colliding, grinding down into finer and finer particles. The ring glows in the star's light, marking out a kind of celestial workshop where new objects can form and old ones are broken apart. Because of its structure and brightness, this debris ring has been a favorite target for astronomers studying how planetary systems grow and change. For a while, it even seemed that a massive planet, nicknamed Fomalhaut B, had been directly imaged within or near the ring. But as more data were gathered, that bright point did not behave like a planet should. Its path and fading brightness suggested something else. Perhaps a large, expanding cloud of dust created by a recent collision between icy bodies. Fomalhaut A's distant companions complete the quiet geometry of the system. One of them, Fomalhaut B, is an orange dwarf, smaller and gentler than our Sun, with roughly 2/3 its mass and a radius just over half as large. Its surface glows at a cooler temperature, giving the star a soft amber tone rather than a hard, white shine. Though it burns steadily, its light is modest. Placed beside the Sun, at the same distance, it would seem dim, almost shy. A warm ember next to a bright flame. Together, these stars form a wide and intricate family. At the center, Fomalhaut A blazes a young, brilliant sun surrounded by a broad ring of dust, where collisions carve new shapes and where planet-like bodies may be forming and fading in slow cycles. Far beyond, its quieter siblings drift on long, looping paths, still held by the same gravitational thread. From Earth, they appear as simple points, faint smudges in a telescope's field. But behind that simplicity rests a layered architecture, a sprawling, stellar household, each member following its own patient rhythm across millions of years, reminding us that even a single bright star in our sky can be an entire world of stories. And from where we stand, the contrast is striking. Our Sun, so familiar and overwhelming in its brightness, outshines many of these nearby stars. Compared to one of Fomalhaut's companions, it is nearly 5 times more luminous. That extra radiance shapes the way our days feel open and full of light. While countless other suns, each with their own planets, dust rings, and quiet histories, remain mere glimmers in our night, waiting patiently for us to notice. Around Fomalhaut B, the orange dwarf companion to the bright primary, astronomers have found hints that there may be a large planet in orbit. Careful studies of its spectrum and motion suggest a companion with a mass in the broad neighborhood of Jupiter's. The evidence is still young. No one has yet traced its path in detail, but if the planet is real, it likely circles its star on a wide, slow orbit, taking roughly 1/4 of a century to complete one long year. In the calm orange light of that dwarf, such a world would be a distant, cold sentinel, moving almost imperceptibly across the centuries. The third star tied into the Fomalhaut family is LP 876-10, a small red dwarf sitting about 2.5 light-years from the main component. It is faint and cool, with a mass only a fraction of the Sun's and a surface temperature just over 3000 Kelvin. Where Fomalhaut A blazes hot and bright, this little star glows softly. LP 876-10 orbits the main star from a tremendous distance, so far out that it takes on the order of 20 million years to complete a single loop. Since the system first formed, this red dwarf would have circled its brighter sibling only a few dozen times. No planets have yet been found around LP 876-10, but the starlight tells us something else. There are signs of a surrounding cloud of gas and dust, stretching outward across a region that could span from 10 to 40 times the Earth-Sun distance. In that broad, cold halo, grains collide and clump, and larger bodies may lurk unseen. From there, you can let your thoughts glide farther to a star that dominates the northern sky with a different kind of light. About 37 light-years away shines Arcturus, the brightest star you can see from the northern hemisphere and one of the brightest anywhere in the night. Its orange glow has been part of human stories for a very long time. Arcturus is the main member of a binary system, though its companion is so faint and so close to the primary that it is almost completely drowned in its glare. The star itself is an orange giant, a sun that has left behind the quieter middle years of its life. Long ago, Arcturus would have looked more like our own star, similar in mass, only slightly heavier, quietly fusing hydrogen in its core. Over billions of years, that hydrogen has been spent. As the fuel in the core ran low, the balance between inward gravity and outward pressure shifted. The outer layers swelled and cooled, turning the star into the giant we see now. Although Arcturus's surface is cooler than the Sun's, it shines far more intensely. Its large size makes up for its lower temperature, and it emits well over 100 times the luminous energy of our star. Its radius is now about 25 times the Sun's, meaning that if you placed it at the center of our system, its outer layers would extend into the region where the inner planets now circle. According to our current understanding of stellar evolution, the Sun, too, will one day exhaust the hydrogen in its core and swell into a giant. The details will differ, but the broad outline is the same: a quiet middle age, a bright, swollen old age, then a gradual shedding of the outer layers. For Arcturus, this process is already underway. At some point, in the not-so-distant astronomical future, it will cast off its outer envelope and leave behind a hot, compact white dwarf that slowly cools over billions of years. Arcturus is also part of a stream of stars moving together through the galaxy, thought to be the remnant of a small galaxy that the Milky Way absorbed long ago. Most of the members of this stream are faint and quiet, lacking the dramatic brightness of Arcturus itself. But together, they hint at how our galaxy grows by gently pulling in smaller neighbors over immense spans of time. If any planets once circled close around Arcturus, they would have faced a harsh fate. As the star expanded, its outer layers would have swelled outward, potentially engulfing any inner worlds. Those that survived farther out would now orbit a very different sun under a redder, more intense light. So far, no planets have been confirmed in the Arcturus system, and the faint companion star, with its much lower luminosity, remains difficult to study in detail. From the cool, steady orange of Arcturus, it is a short step in imagination to another kind of star entirely, a modest yellow dwarf in the constellation of Phoenix, noticed in routine surveys of the sky and now known as WASP 96. For years, it was simply one more unremarkable sun among many. until a network of telescopes designed to look for transiting planets saw its light dip in a rhythmic way. Around 2013, astronomers using the Super WASP survey found signs that a large, puffy planet was passing regularly in front of WASP 9.6 from our point of view. Every few days, the star's light dipped by a tiny amount as the planet crossed its face, and from the pattern of those dips, they inferred the presence of a gas giant. This world, later named WASP 9.6b, orbits extremely close to its star, so close that it completes a full circuit in just a few Earth days. Bathed in intense starlight, its atmosphere swells and heats, making it very low in density, more like a hot, inflated bubble than a compact ball. By studying how the starlight filters through the planet's atmosphere during these transits, astronomers can learn what that atmosphere is made of. Early observations of WASP 9.6b's spectrum showed strong, clear signatures of sodium. That alone was intriguing. In models of gas giants, sodium tends to hide deeper down, below higher, cloudier layers. Seeing its signature so plainly implied that the upper atmosphere might be unusually clean and cloud-free, allowing us to peer farther into the planet's structure than usual. Based on those first measurements, WASP 9.6b was described as having a remarkably clear atmosphere, almost like a pane of tinted glass around a glowing interior. It became a tempting target for a new kind of eye on the sky, the James Webb Space Telescope. The story of James Webb began in the mid-1990s, when scientists and engineers started planning a successor to the Hubble Space Telescope, an observatory especially sensitive to infrared light, the long wavelengths emitted by cool dust, distant galaxies, and the atmospheres of exoplanets. Building such a telescope was a long, careful undertaking. Over about 25 years, its design was refined, its mirrors constructed and polished, its instruments assembled and tested. At the end of 2021, this delicate machine was launched into space. Unlike Hubble, which circles relatively close to Earth, the James Webb Space Telescope was sent much farther out, to a point about 1.5 million kilometers away, near a region of gravitational balance called the second Lagrange point. There, it can keep the Sun, Earth, and Moon all on the same side while it looks outward into the deeper dark. Because its instruments are so sensitive to heat, the telescope must stay extremely cold. To help with this, it carries a multi-layered sun shield that unfolds in space and blocks the warmth and light of nearby bodies. Behind that shield, the mirrors and detectors sit in deep chill, ready to catch the faintest whispers of infrared light from very distant, very old, or very subtle objects. Once it began its scientific work, James Webb quickly started returning images and spectra that felt like opening a new set of eyes. Some of what it showed matched our expectations: swirling star-forming regions, ancient galaxies whose light has been stretched by the expansion of the universe, delicate rings and disks of dust. Other results raised new questions, reminding us that our models are only approximations of a reality that often turns out to be more complex. One of the first exoplanets James Webb examined in detail was WASP 9.6b. Given its reputation as a cloud-free giant, it seemed like an ideal place for Webb's instruments to peer deep into an atmosphere and test their capabilities. As the planet passed in front of its star, the telescope recorded how the starlight dimmed at different wavelengths, creating a kind of barcode of the gases in the planet's outer layers. The new spectrum was richer than anything seen before for this world. Embedded in the data were clear signs of water vapor and the way the light was absorbed and scattered. suggested the presence of hazes or clouds high in the atmosphere, exactly the sort of thing earlier observations had seemed to rule out. Instead of confirming a perfectly clear sky, James Webb painted a picture of a more layered atmosphere, where clouds and mists form and scatter light, reshaping the temperatures and structures deeper down. Earlier estimates of the planet's temperature profile, built on simpler assumptions, suddenly looked more like a rough sketch than a finished map. Not exactly wrong, but incomplete, missing the finer strokes that Webb could now add. When two sets of observations disagree like this, it doesn't always mean one of them must be thrown away. Often it simply means that the story is more complicated than we first thought. With WASP 96b, the early data whispered of a clean, cloudless atmosphere, while Webb's more sensitive gaze revealed water vapor and hazes drifting higher up. Perhaps the first measurements were too coarse, or we read them with too eager an eye. Perhaps there is some subtle behavior in those hot layers of gas that we haven't quite grasped yet. For many scientists, that tension is a quiet thrill rather than a disappointment. It shows that even in a system we thought we understood fairly well, there are still surprises waiting when we look more closely. WASP 96b, with its swollen, overheated atmosphere and rushing orbit, is not a place anyone would wish to visit. But as a laboratory hanging in the sky, it has already reminded us that the universe rarely matches our neat diagrams for long, and that the work of understanding it is really a series of gentle corrections, looking again and again, and letting each new detail soften and deepen the picture we thought we had. James Webb's attention doesn't rest on a single world. About 69 light-years away, its instruments have studied a small, strange family of brown dwarfs objects, too massive to be called planets, yet too small to ignite the long, steady fusion that powers true stars. Brown dwarfs glow faintly with the heat of their own formation, but in visible light, they are easily lost in the dark. In infrared, where James Webb sees most clearly, they stand out like warm embers on a cold night. In this particular system, two of the brown dwarfs orbit close together, only a couple of astronomical units apart, sharing a combined mass slightly above 100 Jupiters. Their temperatures are high by our standards, more than 2000 Kelvin, their outer layers hotter than molten rock. Farther out, at a distance of about 100 astronomical units, a third, lighter companion circles the pair. It is smaller, with a mass somewhere between 14 and 23 Jupiters, and cooler, its outer layers, hovering around 1200 Kelvin, still glowing hot, yet much gentler than its siblings. What makes this outer dwarf especially intriguing is what its atmosphere contains. Alongside the expected water, methane, and carbon dioxide, James Webb's spectrum reveals tiny particles of silicate materials related to quartz and other silicon-bearing minerals. These grains seem to be suspended high in the atmosphere as immense cloud decks, turning the brown dwarf sky into a place of mineral mists rather than water clouds. The idea that such silicate clouds might exist had been suggested for years in models, because silicon is a common product of stellar furnaces, but until now, the evidence had been indirect. Here, for the first time, we are seeing these exotic weather systems more directly. Looking back in time, astronomers think that about 140 million years ago, there was only one large cloud of gas and dust where this system now resides. Under the pull of gravity, it began to collapse. Then, perhaps nudged by the passing weight of another massive object, it fragmented into 3 clumps instead of one. Each clump went on to form a brown dwarf. If the cloud had stayed together, its combined mass might have been just enough to cross the threshold into stardom. Instead of 3 faint, under-fired embers, there might have been a single, small star shining steadily. It is a reminder of how thin the line can be between different kinds of objects, and how small differences in the beginning can lead to very different outcomes. James Webb is just as comfortable with grand structures as with lonely, faint points. One of the most spectacular regions it has turned toward is the Carina Nebula, a vast, star-forming complex about 8,500 light-years away. In ordinary images, Carina appears as a tangle of glowing gas and dark dust, lit from within by young, massive stars. In infrared, much of the obscuring dust becomes more transparent, revealing crowds of stars that were once hidden. Carina is sometimes called a stellar nursery, and the name fits. Within its clouds are thousands of stars in different stages of life, from small, newly formed suns to some of the most luminous and massive stars in the Milky Way, including Eta Carinae and WR25, each shining millions of times brighter than the Sunday. Their fierce winds and radiation carve cavities and pillars in the surrounding gas, shaping the next generation of stars even as they blaze. According to our current understanding, stars form when gravity slowly pulls together clumps of gas and dust, compressing them until they heat and ignite nuclear fusion at their cores. This basic story has been confirmed many times, but the fine details, how turbulence, magnetic fields, and radiation interact, how disks and jets and outflows all fit together, are still being worked out. The full process can take millions of years, yet some of the most critical transitions may happen in bursts that last only hours or days. In the Carina Nebula, James Webb has identified thousands of protostars and young stars, all born from the same large cloud, sharing similar ages and compositions. By watching so many of them at once, astronomers can piece together a more continuous picture of star formation, catching objects at different moments along the path, from cold clump to shining sun. With Webb's sensitivity, there is even a chance of capturing some of those brief, predicted phases. A sudden flare as a young star gobbles a bit more material, a jet bursting through a cocoon of dust, a newborn star shrugging off its last veils of gas. The telescope's great segmented mirror, over 6 meters across, and its finely tuned instruments also allow it to collect light from much farther away, near the limits of what we can see. Some of the galaxies it studies are so distant that their light has been traveling for more than 13 billion years, carrying information from a time shortly after the universe's beginning. Even for Webb, these sources are faint beyond imagination. To detect them at all, nature sometimes has to lend a hand. That help comes from gravitational lensing, a phenomenon predicted by general relativity and confirmed many times over. When a very massive object, a cluster of galaxies, for instance, sits between us and a more distant light source, its gravity warps space-time enough to bend the path of the background light. The cluster acts like a cosmic lens, magnifying and stretching the image of the distant galaxy behind it. The alignment has to be just right, and the conditions are rare, but when they occur, they can boost an otherwise invisible object into view. In one deep observation of a galaxy cluster known as SMACS 0723, about 4 billion light-years away, James Webb detected light from a background galaxy that had passed through such gravitational lenses not just once, but 3 times. Each lensing event magnified and refocused the light until, in total, its brightness was enhanced roughly 20-fold. Without that amplification, the galaxy's glow would have been lost in the background. As it is, astronomers can study the light of a system believed to be around 13 billion years old, an island of stars formed when the universe was still very young. Alongside this galaxy, Webb sees about 10 other compact ancient clusters, likely born a few 100 million years after the beginning, during the era when the first generations of stars and galaxies were taking shape. Their structures appear more complex than some models had expected, suggesting that even in these early times, gravity and gas were already weaving intricate patterns. Such observations will help refine our ideas about how fast the universe grew from its initial simplicity into the richly structured cosmos we see now. They may even hint that our estimates of certain cosmic timescales need adjusting. For the moment, though, what they offer most strongly is a sense of continuity, that the light reaching us tonight left its sources when the universe was still in its childhood. From these great distances and ancient epochs, thoughts can return to something both more familiar and more exotic: worlds of water. The idea of ocean, planets, worlds, covered entirely by deep global seas, began to take clearer theoretical shape in the 1970 seconds. Scientists realized that even far from a star, internal heat from radioactive decay and the constant kneading effect of tidal forces could melt ice hidden beneath frozen surfaces. In our own system, moons like Europa and Enceladus likely host such subsurface oceans, their waters kept liquid under thick shells of ice. When astronomers speak of true ocean planets, though, they usually mean something a little different: worlds where the water is not confined under an icy lid, but flows openly at the surface, forming oceans that can be 100 kilometers deep or more. On Earth, by comparison, all the water in our global ocean makes up only a tiny fraction of the planet's mass. You can think of it as a thin blue skin. On an ocean planet, water would be a major component, a deep, layered mantle between rock below and sky above. In the early 2000s, a group of French astrophysicists, led by Christophe Sautin, explored how such planets might form. Their calculations suggested that if a growing planet in a young system stays below about 10 Earth masses, it will not pull in huge amounts of hydrogen and helium from the surrounding cloud. Instead, if its mass falls in a range of roughly 6 to 8 Earth masses, it may collect large amounts of ice and rock in similar proportions. If such a world remains far from its star, it might become a cold super-Earth or an ice giant with a frozen surface and, perhaps, a hidden internal ocean warmed from within by radioactive decay. But if that same planet drifts or forms closer in, settling into the star's habitable zone, the story changes. The outer layers of ice can melt, not just in patches, but completely, pouring across the surface to form a deep, global ocean. There would be no continents in the way we know them, only water and whatever structures rise from the deep. Beneath that ocean, at great pressures, ice can exist in exotic forms, different from the familiar frost on a window pane. Above, an atmosphere rich in water vapor and other gases would interact with the star's light, shaping weather patterns and climates very unlike our own. These ideas remain, for now, mostly on paper and in computer models, supported by hints from exoplanet surveys that have found many worlds in the right mass range and at the right distances. We have not yet seen an ocean planet in a way that lets us say with certainty that its surface is entirely water. But as telescopes like James Webb continue to study exoplanet atmospheres and compositions, the chances grow that one day we will be able to point to a dim star in the sky and know that around it circles a world where there is nothing but ocean from one horizon to the other, rocking gently under an alien sun. When astronomers run the numbers for an ocean world, the results are both precise and dreamlike. A planet 6 to 8 times the mass of Earth could, in principle, carry a global layer of water more than 100 kilometers deep. Under that much ocean, the pressure at the bottom would climb to tens of thousands of times the pressure at sea level on Earth. In that hidden darkness, water stops behaving the way we know it. It can freeze into exotic forms of ice that stay solid even at temperatures where ordinary ice would long since have melted. These high-pressure ices are heavier than liquid water and sink instead of floating. One of them, called Ice 7, is expected to form at such depths, with a density around 1,650 kilograms per cubic meter. On an ocean planet, that kind of ice would settle onto the seafloor, forming a thick, solid shell, a cryosphere that wraps around the rocky core below. Above it, an ocean. Above the ocean, sky. For a long time, these worlds were mostly equations and models. Then a small, dim, red star, about 42 light-years away, came into focus. It is known as GJ 1214, a red dwarf with a diameter roughly 5 times smaller than the Sun's and a mass only about 1/6 as large. It is about 300 times dimmer than our star, with a surface temperature near 3000 Kelvin, a cool ember compared to the Sun's blaze. On its own, it would be just another of the countless red dwarfs scattered through the galaxy, easy to overlook. In 2009, however, astronomers found that GJ 1214 hosts a planet, GJ 1214b. As it passes in front of its star from our point of view, it causes tiny, regular dips in the starlight, a clue that something substantial is there, blocking a fraction of the glow. From those dips and follow-up measurements, a picture emerged. The planet's diameter is about 2.5 times that of Earth, and its mass is about 6.5 Earth masses. That combination gives an average surface gravity slightly lower than Earth's, around 90% of what you feel when you stand on the ground here. More telling is its average density, about 1,870 kilograms per cubic meter. Earth, made mostly of rock and metal, is much denser. GJ 1214b's lower density suggests it cannot be built mostly from the same materials. Instead, the numbers fit better with a composition dominated by water and various forms of ice, perhaps 3/4 water and ice, 1/4 rock. In other words, an ocean planet seems not just possible here, but likely. The planet's orbit hugs its star very tightly. On average, it circles only about 2 million kilometers away, roughly 0.014 astronomical units, a separation more than 70 times smaller than the distance between Earth and the Sunday. Its orbit is also somewhat elongated, so that at its closest, it is nearly twice as near to its star as it is at its farthest. 1 year on GJ 1214b lasts only about a day and a half by our clocks. Even though its star is faint compared to the Sun, such closeness means the planet is bathed in intense radiation. If its surface reflects light about as well as Venus does, calculations suggest an equilibrium temperature around 393 Kelvin, about 120 degrees Celsius. If the surface is darker, it could be much hotter, climbing toward 553 Kelvin, where conditions are more like the inside of an industrial furnace than any earthly sea. Because GJ 1214b crosses the disk of its star from our line of sight, astronomers can study its atmosphere using spectroscopy. As the planet passes in front, a thin slice of starlight filters through the gases around it. Different molecules absorb light at specific wavelengths, leaving a pattern in the spectrum that can be read like a barcode to reveal what the atmosphere contains. If GJ1214b is truly an ocean planet with a deep water layer, its atmosphere might be expected to be rich in water vapor with traces of other gases. But when researchers looked, the spectrum refused to give simple answers. Clear signs of hydrogen, helium, water, carbon dioxide, or ammonia did not appear as expected. Instead, the data suggest a thick, opaque outer layer, perhaps a haze or cloud deck, that hides the true composition underneath. The atmosphere seems to be veiling itself. The conditions imagined at the surface are extreme. The lower atmosphere may reach pressures at least 15 times higher than at Earth's sea level, with temperatures like those in a giant steam boiler. The boundary between ocean and air blurs because the water vapor just above the surface can be almost as dense as the boiling water beneath it. Instead of a sharp line where sea ends and sky begins, there is a deep region where fluid and gas trade places in a dense, hot mix. Deeper still, as you descend through the imagined ocean, the pressure continues to climb. Around 100 kilometers down, the conditions would push water past its familiar liquid state into those exotic high-pressure ices. There, the bottom would not be rock, but dense, heavy ice, perhaps thousands of kilometers thick. Most of the planet's water would be locked in that inner shell, with only a thinner, though still enormous, liquid layer above. Beneath the ice, at the very center, would lie the rocky and metallic core. For all their beauty and strangeness, such worlds may not be friendly to life as we know it. Even on cooler ocean planets, where surface temperatures might be kinder, the chemistry can be poor in the trace elements that living cells need. With no continents or exposed rock for rain to wash over, fewer minerals dissolve into the sea. Meteorites can deliver some variety, but perhaps not enough. The vast, deep oceans could remain simple in composition, their waters lacking the rich mix of ingredients that helped life arise on Earth. Still, these planets are scientifically precious. They offer a laboratory for understanding how water behaves under extreme conditions and how planets grow and change when water is not just a thin layer, but a major structural component, and they may be far from rare. In 2020, NASA-supported modeling suggested that there could be billions of such worlds in our galaxy alone, some cold, with oceans hidden beneath ice shells, others warm, like GJ1214b, wrapped in thick, steamy atmospheres. Water, after all, is one of the most common complex molecules in the universe. Where there is plenty of material, it is natural for it to gather. All of this unfolds against a backdrop of discovery that has accelerated over just a few human decades. The first exoplanets, planets orbiting other stars, were confirmed in the late 1980 seconds and early 1990 seconds. Since then, every new generation of instruments has widened our view. By early 2021, astronomers had cataloged more than 4,000 confirmed exoplanets, with several thousand additional candidates waiting for confirmation. Each new detection is a small shift in our understanding of how typical or how unusual our own solar system might be. Estimates suggest that there could be more than 1 trillion planets in the Milky Way. A significant fraction, perhaps between 5 and 20%, are likely similar to Earth in size and basic composition. Not all of those live in the so-called habitable zones of their stars, the regions where surface water could remain liquid. Even so, When the numbers are scaled up across an entire galaxy, they imply that there may be hundreds of millions of potentially habitable planets scattered among the stars. The variety among known exoplanets is already staggering. Some are giants larger than Jupiter, skimming so close to their stars that their atmospheres glow and boil away. Others are small, compact worlds not much bigger than Earth. There are planets locked in deep freeze, encased in permanent ice. There are worlds with oceans of molten rock, where the surface is not water but lava. Some skies may rain sulfuric acid. On others, the pressure and chemistry could allow carbon to crystallize and fall as diamond snow. And then there are the ocean worlds, with no continents at all, only an unbroken expanse of water rolling beneath unfamiliar constellations. Our instruments and our patience are only beginning to catch up with the richness hinted at by these discoveries. For now, we float here on our own small blue planet, listening to faint signals from distant systems and slowly learning how diverse a world can be. Finding other worlds is a delicate art. Even with powerful telescopes, a planet next to its star is like a firefly beside a lighthouse. Its own light is drowned in the glare. Most of the time, we can't simply look and see a planet as a separate point. Instead, astronomers watch for subtler signs, small changes in starlight that hint at a hidden companion. To make that kind of watching easier, a special space telescope was launched in 2009, Kepler. It was the first observatory, built with one main purpose in mind: searching for planets beyond our solar system. Kepler's camera was made of 42 light-sensitive detectors, working together like a vast, gently staring eye with nearly 100 million pixels. Coupled with a mirror about 1.5 meters across, it could monitor a large patch of sky and pick up minute variations in starlight. Kepler's field of view covered a significant slice of the heavens, and within that wedge of space, it could notice the faintest dips in brightness, from stars up to about 3,000 light-years away. During a little over 3.5 years of its most productive observing time, it recorded signals from more than 150,000 stars and flagged over 3,000 possible exoplanets. Many of those candidates have since been confirmed, more than 2,000 worlds whose existence has been cemented by careful, repeated checks. Among them, Kepler revealed some remarkable extremes. One was Kepler 37b, the smallest known exoplanet at the time of its discovery, with a diameter just over a third that of Earth, more like our moon in size than our own planet. Kepler also noticed dim companions like brown dwarfs and added new stars to our catalog, but its main gift was the sheer number of planets it showed us all at once. The method Kepler used is called the transit method. Instead of trying to see a planet directly, it watches a star's brightness. When a planet passes in front of its star, as seen from our vantage point, it blocks a small fraction of the starlight. To us, the star seems to blink ever so slightly, dipping in brightness in a regular pattern. The depth of the dip tells us how big the planet is compared to the star. The spacing between dips reveals how long the planet takes to orbit. These changes are tiny. The drop in brightness may be less than 2%, often just a few tenths or hundredths of a percent, like dimming a lamp by a barely noticeable amount. From the surface of Earth, such subtle shifts are easily disturbed by our own atmosphere. Air currents, dust, humidity, even thin clouds all cause stars to twinkle and fade in ways that can mask or mimic planetary transits. That is why space-based telescopes are so valuable for this work. Freed from the turbulence of air, they can watch stars with calm, steady eyes. Kepler did this beautifully until 2013, when mechanical failures in its orientation system made it impossible for the telescope to keep pointing as precisely as before. Ingenious workarounds extended its life for a while in a modified mission, but by 2018, its fuel was exhausted, and its scientific operations came to an end. By then, it had changed our understanding of the galaxy, showing that planets are not rare jewels, but common companions. Most of the worlds Kepler found, however, were relatively far away and dim from our point of view. They were wonderful for statistics, for learning how common planets are, what sizes and orbits they prefer, but many were too distant for us to study their atmospheres or surfaces in detail. The next major mission in this story was designed a little differently. In April 2018, NASA launched TESS, the Transiting Exoplanet Survey Satellite. Where Kepler had stared at one patch of sky, TESS was built to sweep across almost the whole dome around us. Its task is to look for rocky, Earth-sized planets orbiting bright nearby stars within a couple of hundred light-years. Nearby, stars are easier to study later with larger telescopes, so the planets TESS finds become promising targets for further exploration. TESS uses the same basic technique as Kepler, watching for tiny dips in starlight when a planet passes in front of its star. It carries 4 small telescopes, each with a wide, square field of view. Together, they can monitor broad strips of the sky, first in one hemisphere and then in the other, eventually covering about 85% of the celestial sphere. The cameras collect images with high enough precision to catch the telltale regular dimmings that signal a transit. One of the most intriguing systems TESS has brought into focus is centered on a small red dwarf star called TOI 700, a little over 100 light-years away. TOI stands for TESS, Object of Interest, a reminder that each new candidate begins as a modest pattern in a dataset before it becomes a confirmed world in our catalog. TOI 700 is cooler and smaller than the Sunday. Its surface temperature is roughly half of ours, and both its mass and radius are about 40% of the Sun's. In visible light, it would appear much fainter, casting a softer, redder glow. One of its quiet strengths is its stability. Since observations began, no significant flares have been recorded. For planets hugging close to small stars, this calmness matters. Frequent flares can strip atmospheres, bathe surfaces in harsh radiation, and make it harder for any fragile chemistry to persist. Around TOI 700, at least 3 planets have been found. The innermost, TOI 700b, is similar to Earth in size. Its mass is estimated to be only slightly higher than our planet's, about 7% more, and its radius differs by less than a few percent. But size alone does not make a world comfortable. TOI 700b orbits very close to its star, at a distance of only a few hundredths of an astronomical unit. One of its years lasts about 10 Earth days. So close to a dim red dwarf, the planet is still likely to be quite hot. It is also probably tidally locked, keeping the same face toward its star at all times, much like the Moon does with Earth. One hemisphere would endure endless daylight, the star fixed in the sky. The other would sit in eternal night. The stark contrast between those sides, coupled with the intense stellar heating, makes it an unlikely place for gentle seas and mild breezes. Farther out lies TOI 700c, a world thought to be a mini Neptune. Its mass is several times that of Earth, perhaps between 5 and 13 Earth masses, and its radius is roughly 2 to 3 times larger. Those proportions suggest a thick envelope of gas around a denser core, more like a small gas giant than a rocky planet. It completes an orbit in about 16 days and sits closer to the star than the inner edge of the habitable zone, bathed in more energy than a temperate planet would receive. Its skies, if you could stand somewhere solid, would likely be bright and hot, with deep layers of atmosphere swirling above. The third known planet, TOI 700d, is the one that has drawn the most attention. It orbits near the inner edge of the star's habitable zone, the range where, in principle, liquid water could exist on the surface of a rocky planet. Its year lasts about 37 days, and its distance from the star gives it an energy input about 86% of what Earth receives from the Sunday. That is less, but not dramatically so. The estimates for its mass range from roughly Earth-like to about 3 times heavier. Its radius seems to be a little larger than Earth's, by about 20 to 30%. Those measurements fit with the idea that TOI 700d is a rocky world, though the exact proportions of metal, rock, and possible ices are not known. If its atmosphere were similar to ours, simple calculations suggest a global average temperature a few degrees below freezing cold, but within reach of more comfortable conditions if greenhouse gases or other atmospheric features helped trap additional heat. We do not yet know the exact shape of TOI 700d's orbit, but it appears to be only slightly elongated, with a low eccentricity. Even so, being right on the inner edge of the habitable zone means that small variations in distance from the star can have noticeable effects. When the planet moves a little closer, it briefly experiences more intense heating, perhaps nudging parts of its environment above or below key thresholds over long timescales. Such subtle shifts could matter for climate and for the stability of any surface water. Taken together, the TOI 700 system offers a kind of miniature gallery, a hot, tidally locked Earth-sized inner world, a puffier, gaseous middle planet, and an outer, slightly larger rocky planet, hovering in a region where the light is neither overwhelmingly fierce nor hopelessly weak. All of them circle a small, steady red star, far away and yet close enough in cosmic terms that our instruments can catch the tiny shadows they cast. In the quiet of the night, it can be strangely soothing to remember that such systems exist at all little families of worlds orbiting their suns, each with its own rhythm, its own balance of light and dark, quietly turning while we listen from our small, bright corner. On TOI 700d, a year passes in a little more than a month by our measure. Any times when the planet slips slightly closer to its star and the heat becomes harsher would come and go on that rhythm, brief seasons, not endless ages. If life exists there in some form, it might survive those bright spells by slowing itself down, slipping into something like a quiet dormancy until conditions soften again. Or perhaps it would drift toward regions where the climate stays more forgiving, learning to follow the gentler zones around the planet. The data we have so far, drawn from the faint fingerprints in the starlight, is far from enough to make firm claims. But there is room, within the uncertainties, for liquid water to exist on the surface of TOI 700d. If that is true, then some kind of greenhouse effect is likely as well, trapping part of the star's warmth and nudging the surface temperature into a range friendlier than the bare numbers first suggest. Like its siblings in the system, TOI 700d is probably tidally locked, always showing the same face to its star. On such a world, the day side and night side would be profoundly different. One hemisphere would sit under a sun that never sets, while the opposite half would never see dawn. The temperature contrast between those two faces would be stark. If the planet has a thick atmosphere, winds would howl from hot to cold, trying to even things out. Great, continuous streams of air transporting heat toward the dark. The result could be a world wrapped in powerful, constant winds, with a band of twilight circling the line between day and night, where conditions might be most moderate. While we imagine these possibilities, TESS continues its patient work. Its main mission is complete, but it still has fuel and functioning instruments, and it keeps on taking images of the sky, including the densely populated plain of the Milky Way, where stars crowd together and searches become more challenging. In its surveys, TESS has already found more than 2,000 exoplanet candidates, dozens of which have been confirmed as real worlds. Along the way, it has also caught the sudden flares of distant supernovae, the subtle signatures of exocomets, and the motions of small bodies in our own solar system, extra gifts gathered while it was looking for planets. TOI 700D remains, for now, a distant silhouette. Much of the hope for learning more about it rests with larger, more sensitive instruments like the James Webb Space Telescope. With its ability to read the faint spectra of exoplanet atmospheres and to tease out tiny details in the light from nearby stars, Webb offers a path toward seeing not just the presence of such planets, but hints of their skies and surfaces. Worlds like TOI 700D, along with many others, wait in its growing list of targets, quiet destinations for a telescope that listens in infrared. From these relatively nearby systems, the mind can drift outward to scales where distances start to feel almost abstract. Between our galaxy and others, the gaps are measured not in light minutes or light hours, but in millions and billions of light years. Because the universe is expanding, the space between us and remote galaxies is stretching, and the light they send arrives with its wavelengths pulled longer, shifted toward the red. This red shift is more than a color change. It carries information about how far the light has traveled and how fast the distant object is receding. Not every galaxy is moving away from us, though. On smaller scales, gravity still gathers and pulls. Some galaxies show a blue shift in their spectra, meaning they are drifting toward us rather than fleeing. One such traveler is M86, a large galaxy in the Virgo cluster. It lies about 50 million light-years from the Sun and is moving inward through the cluster at hundreds of kilometers per second, headed roughly in our direction on that local stage. As M86 plows through the thin gas that fills the cluster, it loses some of its own interstellar material. The galaxy leaves behind long, glowing filaments of warm, ionized hydrogen, delicate streams of gas that trace its passage like contrails in the sky. M86 is linked by some of these filaments to a heavily disturbed spiral neighbor, NGC 4438. Evidence suggests that the two galaxies interacted in the past, a close encounter or collision that stripped material from the smaller spiral and helped shape the trails we see today. M86 bears other scars as well. In the faint outer halo around it, astronomers have detected multiple stellar streams, stretched out rivers of stars that likely represent the remains of smaller galaxies torn apart and absorbed long ago. The galaxy also hosts an unusually large number of globular clusters, dense spherical swarms of ancient stars. There may be nearly 4,000 of these clusters in M86, many times more than in the Milky Way. One idea is that some of these clusters are the preserved cores of dwarf galaxies that were once separate, later swallowed by M86 in a long, slow act of galactic eating. Despite these dramatic details, M86 is not unique. Another galaxy, ESO 137-001, has a similar basic shape, but tells its own striking story. Located more than 200 million light-years from the Sun, it lives in a rich cluster of galaxies known as Abell 3627 and is falling toward the cluster's center at a remarkable speed, approaching 2,000 kilometers per second. As ESO 137-001 rushes through the hot, thin gas that pervades the cluster, it experiences a strong ram pressure, the same kind of force you feel when you stick your hand out of a car window at high speed, but on a vastly larger scale. This pressure strips gas from the galaxy, blowing it backward and forming long tails that trail behind it for hundreds of thousands of light-years. Observations show that the mass of gas in these tails can be several times greater than the gas left within the galaxy itself. In those stripped streams, new stars are still forming. Hydrogen clouds in the tails collapse into fresh star clusters, so that even as ESO 137-001 loses the raw material for star formation in its main body, it leaves behind chains of young, blue stars glowing in its wake. Seen from the side, with its luminous core and its long, wispy trails, the galaxy resembles a giant jellyfish drifting through the dark sea of space. Over time, the continued loss of gas means that ESO 137-001's own star-making ability will dwindle. Without enough cool interstellar material, its spiral arms will fade, and its structure will settle into a quieter shape. Yet this process offers astronomers a chance to learn. By watching how the gas tails behave and how they move in the cluster's gravitational field, researchers can infer the distribution of mass, including dark matter, which does not emit light but still exerts gravity. If stripped gas tails and glowing filaments are one way for stars to be born, there are others far more intense. Among the most dramatic examples known is a galaxy informally called the Baby Boom Galaxy. Its name hints at what is happening there, an astonishing burst of star formation. In this system, thousands of new stars are thought to ignite every year, hundreds of times the rate in the Milky Way. Averaged out, it is as if a new star lights up every couple of hours. The Baby Boom Galaxy is not nearby. Its light has traveled roughly 12 billion light-years to reach us, meaning that we see it as it was when the universe was only about 1.5 billion years old. At that time, the cosmic web of matter was still settling into the large-scale structure we recognize today. According to many models, galaxies in that era should be building up their stars, but perhaps in a more gradual way. Baby Boom, with its frenetic activity, seems to be running ahead of schedule. Looking at such a galaxy is like catching a glimpse of a crowded, early city in the cosmos. Stars packed together, gas being consumed quickly, the future shape of the system being decided in a relatively short burst. Over the billions of years since that light left, the galaxy will have changed, perhaps quieted, perhaps merged with others. We cannot see its present self, only its distant past. But even that single snapshot tells us that the universe has, from early on, been capable of both calm and extremes, gentle, slow star formation in some places, and wild, rapid bursts in others. In the quiet where you are now, all of this can feel very far away. Blue shifted galaxies, jellyfish-shaped spirals, starburst cities 12 billion light-years distant. Yet their light is here, mixed into the starlight that reaches our telescopes, and sometimes into the images that drift across your screen. They are part of the same universe that holds your own small world, turning slowly under its local star while you listen and imagine. In places like the baby boom galaxy, stars are being born at a rate that almost defies our intuition, and we still don't fully understand why. Something in its gas, its collisions, its gravity has tuned that region of the universe into a furious nursery where new suns ignite by the thousands each year. Whatever the underlying cause, it offers a rare window into how galaxies behaved when the universe was young, how quickly they could build their stellar populations, how wildly they could blaze in their first bright ages. From that distant, crowded city of stars, it feels soothing to turn to a galaxy you can, in principle, glimpse with a simple amateur telescope. M104, the Sombrero Galaxy, sits about 30 million light-years away. Its name comes from its appearance, a bright, rounded central bulge flanked by a broad, dark band of dust, like the brim of a hat silhouetted against light. That dark ring is not emptiness. It is filled with cold hydrogen and fine dust, raw material for new stars. Observations show that this ring is where many of the galaxy's younger stars are being born, hidden at visible wavelengths but revealed in infrared and radio. Around and within it, the sombrero's structure becomes more intricate. Data from space telescopes sensitive to infrared light suggest that a large portion of its stars form a smooth, rounded component typical of elliptical galaxies made mostly of older, yellow, and red stars. Threaded through this are spiral features, winding arms of younger stars and gas, partly veiled within the broader halo. The picture that emerges is of a hybrid, an elliptical-like body with embedded spiral patterns, perhaps the legacy of a past collision. Two galaxies, once separate, may have drifted together and merged, their stars blending into a single system, while the gas and dust reorganized into the striking ring and hidden arms we see now. It is remarkable that, after such a grand event, the resulting structure is not a chaotic blur, but something stable and elegant enough to study. At the very center of the Sombrero Galaxy, something even more intense seems to be at work. Strong X-ray emission pours from its core, a sign of hot, energetic processes near a compact object. The best explanation is a supermassive black hole surrounded by an accretion disk of infalling gas and dust. As material spirals inward, it heats up and emits high-energy radiation before crossing the point of no return. Estimates put the mass of this black hole at over 1 billion times that of the Sun, making it one of the more massive such objects known. Scattered within the galaxy are also sources of extremely high-frequency radiation, whose exact nature remains uncertain. They may be tied to regions of intense star formation, to compact remnants, or to other energetic processes we do not yet fully understand. In a single galaxy, the Sombrero manages to combine quiet old stars, active nurseries, and a deeply powerful central engine. Another galaxy with an arresting appearance is M64, often called the Black Eye Galaxy. Its nickname comes from a prominent dark band of dust that cuts across its bright central region, giving the impression of a bruised or shadowed eye staring out into space. That band partially hides the core from our view in visible light, adding a sense of mystery to an already dramatic object. M64 is relatively modest in size compared to some giants, with a radius of about 25,000 light-years, and it lies roughly 17 million light-years from the Milky Way. Despite its manageable scale, its internal motions are surprisingly complex. The galaxy is made up of two main components, an inner disk and bulge, and an outer ring. Observations show that these two regions rotate in opposite directions. The inner parts spin one way, the outer ring goes the other. The most plausible explanation is a past merger. Long ago, M64 may have collided with a smaller galaxy that was orbiting in the opposite sense. Over time, the stars and gas of the two systems settled into a single structure, but the gas from the captured galaxy retained its original spin. Now, in the outer regions, that gas and the stars that formed from it move counter to the inner material, like two overlapping wheels turning against each other. For such a finely tuned structure to arise, many conditions would have had to line up. The masses of the colliding galaxies, their approach speeds, the angles of impact. The chance of everything aligning just so is small, and yet here it is, a strange, layered rotation, preserved over millions of years. It is another quiet reminder that the universe has had plenty of time to try all kinds of combinations, and some of them leave behind beautiful, improbable scars. After wandering among galaxies, busy, merging, starbursting, or stripped, it is natural to wonder about something bigger. We talk about centers all the time. The center of the solar system, the center of a galaxy, the center of a cluster. You might ask, very gently, does the universe itself have a center in the same way? In smaller systems, the idea is clear. The solar system's center is not a physical object, but a point where the combined gravity of the Sun and all its planets balances a common center of mass. Because the Sun holds most of the mass, that point lies just under its surface. The Milky Way, too, has a kind of center, a compact region around which its stars orbit, where a supermassive black hole and a dense bulge of stars sit. Galaxy clusters have their own centers of mass, around which their member galaxies move. It is tempting to imagine that if you keep going up in scale, solar system, galaxy, cluster, supercluster, you might eventually arrive at a single pivot point for everything, a grand center for the universe. But when we step back far enough to look at the very large-scale structure, the pattern changes. On these scales, stars gather into galaxies, and galaxies come in a few broad types: spirals with their arms, ellipticals with their smooth, rounded shapes, and irregulars that don't fit neatly into either category. Galaxies themselves form groups and clusters, and these tie together into even larger arrangements called superclusters. Stretching between these are filaments long, thread-like chains of galaxies and gas. Between the filaments lie vast, relatively empty regions known as voids, where very few galaxies reside. Viewed from far away, this network of filaments and voids gives the universe a texture like foam or sponge, dense in some places, almost empty in others. There are certainly regions where gravity has drawn a lot of matter together, places sometimes called great attractors, where clusters and superclusters are slowly drifting, but none of these seem to dominate everything in a way that would make them a true center. Their influence, while strong locally, does not extend across the whole. So far, no object has been found whose gravity shapes the universe on the largest scales. If there were a single massive center pulling everything in, its effects would be hard to hide. Instead, observations suggest something simpler and more subtle. On scales of hundreds of millions of light-years, the universe appears roughly homogeneous and isotropic. It looks, on average, the same everywhere and in every direction. This idea is known as the cosmological principle. In practice, it means that if you could stand in a galaxy billions of light years away and look around, your large-scale view of the cosmos would resemble ours. You would see filaments and voids, clusters and groups, but not a special sign pointing toward a unique middle. From that perspective, there is no preferred place, no cosmic throne at the center. From Earth, when we look outward, we can only see as far as light has had time to travel since the universe became transparent. Because space has been expanding while that light moves, the distance to the most remote objects we can observe today is about 46 billion light-years. Even though the light itself has been on the road for about 13.8 billion years, the region within that distance is called the observable universe, or sometimes the metagalaxy. To us, viewing from here, it naturally forms a sphere with ourselves at the center, simply because we are measuring distance in all directions from our own position. It would be a mistake to take that apparent centrality too literally. Standing on a planet, the horizon draws a circle around you, and it can feel as if you are at the center of the world. In reality, you are just at the center of your own horizon's circle, not of the Earth itself. In the same way, we sit at the center of our observable bubble, not because we are in a privileged cosmic location, but because we are looking out from here. The observable universe might be only a small patch of a much larger whole, or it might span everything that exists. At present, we simply do not know. Light beyond that horizon has not had time to reach us, and may never do so. Within our bubble, the patterns we see suggest that no single point has been singled out as the center in any physical sense. If there is no universal pivot to find, then the question of the center becomes softer, more philosophical. Instead of searching for a special place in space where everything began, we can think in other ways about how expansion itself works, about how every point can be as valid a center as any other, about how a universe without a single middle can still have a story that starts everywhere at once. According to the picture we have today, our universe began about 13.8 billion years ago in a special phase we call the Big Bang. Before that, ideas like before and after, or here and there, don't really work the way we use them in everyday life. It wasn't a fireball exploding into empty space. It was space and time themselves beginning and starting to stretch. When you hear the word bang, it's completely natural to wonder, where did it happen? If something began, surely it must have started at some point in space. There's a quiet itch in that question. To get closer to an answer, we can turn to the traces of the early universe that are still with us now. Two of the clearest traces are the expansion of the universe and the cosmic microwave background, the faint afterglow of the hot early cosmos. If we look carefully at these, we can ask, is there any way to follow them back to a central point? Or is the idea of a single center simply not how this universe works? The expansion we measure is surprisingly even. On very large scales, every distant galaxy seems to be moving away from every other, on average. That tempts us to think, if everything is flying apart, maybe we can measure the speeds and directions and then rewind the motion, letting all the galaxies fall back into one place to the center of the explosion. But when people do that calculation properly, something odd happens. If you trace the motions backward from where we are, the lines do seem to converge near our own location, close to the solar system. That sounds very special, until you realize that if you went to a distant galaxy and did the exact same exercise from there, you would again find the center landing right on top of you. Every observer, no matter where they stand, finds themselves at the middle of the expansion. A softer way to picture this is with a balloon. Imagine drawing a few dots on its surface. At first, the balloon is small, the dots close together. As you blow it up, the surface stretches and the dots move farther apart. None of those dots is sitting at the center of the expansion on the surface. The true center is somewhere in the air, inside the balloon, outside the two-dimensional world of the dots. From the perspective of the dots, each one simply sees all the others moving away as the distance between them grows. In our universe, space itself plays the role of that balloon's surface, but in more dimensions. Galaxies are carried apart not by flying through a pre-existing void, but because the space between them is stretching. In that picture, there isn't a single special point inside space where it all started. The expansion happens everywhere at once. From this comes another idea, the cosmic horizon. Because the expansion makes very distant galaxies recede faster and faster, there's a distance beyond which things are moving away from us faster than light, simply because space is stretching so quickly in between. That doesn't break relativity, because nothing is racing through space faster than light. It's space itself that's enlarging. But the practical effect is the same. Light from beyond that boundary can never catch up to us. Those regions slip permanently out of view. If you stand on Earth and think about that boundary, it draws an imaginary sphere around you. Everything inside is where light has had time to reach you since the universe became transparent, and everything beyond is out of reach. The exact radius depends on the details of our models, but it's well over 14 billion light years. From your vantage point, you sit at the center of that sphere, just because you're measuring outward in all directions from where you are. Someone in a distant galaxy could do the same thing, drawing their own sphere defined by the light that has reached them so far. They would place themselves at the center of their observable universe too. Each point has its own horizon. None of those points is more correct than another. So expansion alone doesn't give us a unique central pivot. The stretching of space happens everywhere, together, like a foam that's swelling throughout its volume, rather than a shell flying away from a single spark. The other great clue is the cosmic microwave background, the CMB. This is a sea of ancient light filling the universe in all directions, the leftover glow from a time when everything was hot and dense and filled with a kind of ionized fog. When the universe cooled enough for protons and electrons to combine into neutral atoms, that fog cleared and light could travel freely. Over billions of years, as space expanded, those photons were stretched into microwaves. Today, they bathe us at a temperature of about 2.7 Kelvin, just a few degrees above absolute zero. For a long time, the CMB was thought to be perfectly uniform. No matter where you looked or in which direction, the temperature appeared the same. That fit nicely with the idea that, on the largest scales, the universe is very smooth. But as measurements became more precise, tiny variations began to show. In some very large, underdense regions, cosmic voids where there are few galaxies, the CMB appears just a tiny fraction of a degree cooler than average. In other places, the background light passes through hot gas or strong gravitational fields and gains or loses a little energy, shifting its color slightly. Our own motion leaves a mark as well. As the Sun and Earth move through space, the CMB looks a bit bluer in the direction we're traveling and redder behind us, a gentle Doppler effect written on the ancient glow. All of these effects are what scientists call secondary anisotropies. They don't tell us about the first instant of the universe. They tell us about later interactions, light passing through clusters, voids, and around massive objects, and about our own motion. Underneath those layers, there are also very subtle primary patterns in the CMB itself, tiny hot and cold spots that reflect slight differences in density in the early universe. Those have been mapped and studied in detail, and they help explain how today's galaxies and clusters grew from small seeds. But if we were hoping for a clear arrow pointing to a single special place, the CMB doesn't provide one. It wraps around us almost evenly, like a softly glowing shell, with no sign that one direction or location is privileged over another. Putting the expansion and the background together, a gentle conclusion emerges. There is no point we can honestly single out as the one true center where everything began. The universe appears to be expanding everywhere, all at once. On the largest scales we can see, no position stands out as the middle, and no direction is marked as toward the heart of it all. That doesn't mean we've seen the whole of existence. What we call the observable universe may be just a small patch of something vastly larger, or it might be all that there is. Our instruments cannot look past our own horizon of light. If there's more beyond, it lies outside the reach of any telescope we can build. Within the part we can see, there are billions of galaxies, each with its own history of stars, planets, gas, dust, collisions, and quiet intervals. Every time a new observatory opens its eyes, the story grows more intricate. New kinds of worlds, new shapes of galaxies, new puzzles to sit with. There is no single center for us to go and find, only countless places to listen to. Where you are right now may be near a window, maybe in a darkened room. The night sky might show only a few scattered points of light, or nothing at all if clouds have drawn a curtain. But beyond that, familiar darkness stretches a universe with no marked edge and no throne at the middle, filled instead with layers of ancient light, slowly arriving after journeys longer than any human lifetime. Those photons don't tell us where the center is. They tell us that the universe has been unfolding everywhere, quietly and steadily, for a very long time, and that the simple fact of you being here, wondering about it in this small corner, is already something tender and strange enough to think about for a while, before sleep finally catches up and carries you off.